next we will look into the computer system organization. So, how are the components of a computer system are organized? So, a modern general purpose computer system, it consists of one or more CPUs and a number of device controllers connected through a common bus that provides access to shared memory. So, what we mean by this is something like that. So, we have got we can have one or more CPUs, like it is so no, ideally the type of interface that we have is there is a CPU and there is a memory chip and there are IO devices that are connected. Now, this type of systems, the basic problem is that at one point of time CPU can do only one job. So, I cannot think of parallelism in terms of programs being executed by the system. So, if there are even if there are multiple users, so I cannot execute their jobs parallelly. I have to do some sort of time sharing. I do user 1's job for some time, then user 2's job for some time, like that. So, that way I can operate in a time multiplexed fashion, but that way performance or the throughput of the system will be low, because the user jobs will take more time for completion. Now, think of a situation where I have got two CPUs instead of one CPU. So, there I have got two CPUs, then at least the two CPUs can do two jobs simultaneously. So, there the number of the programs that these CPUs can execute is just doubled of the actual or previous one. Now, apart from that, we have got a number of devices connected. So, this IO device, then this memory, so all of them are connected. Now, you see this CPU, there are two CPUs, CPU 1 and CPU 2. So, they need to talk to the memory. So, when they send some request for some content of some memory location, so two CPUs may be requesting for content of two memory locations. Now, how to get the data? Okay. So, how to so memory will get confused, because now normally we know in a memory chip we have got address bus, data bus and control bus, and those values coming. So, memory will be responding with the content of the corresponding location. Now, in this case I need to have two address buses, two data buses and two control buses between the CPU 1 to memory and CPU 2 to memory. So, that makes it more difficult. So, we should have something which is additional, which we call the memory controller, or in short I write it as MC. The memory controller should be there. So, all these CPU requests that are coming should be coming to the memory controller, and the memory controller will in turn decides like how to provide service for these requests from the individual CPUs and the data made available to them. So, that so similarly for each and every device that you have in the system, so they will have their own behavior and they need their own controller. Unfortunately or unfortunately, these devices that we have in a computer system, so they are not uniform. So, all of them cannot have same type of interface. For example, the keyboard and mouse and the disk, so they are not having similar type of behavior. So, keyboard the user is pressing some key, on the other hand, and that in that case that key code or the text the text of the key should reach the computer. On the other hand, when the user moves a mouse, the mouse coordinate should reach the computer. Similarly, when you are transferring some data from a disk, then it is actually the data that has to go from the disk to this computer system, and the amount, the volume makes the difference. So, keyboard also, whenever we are typing a pressing some key, the key code is reaching the computer, and when you are in a disk also, so when some transfer is done, there also some data is being transferred, but their nature is different. So, in case of disk it is a voluminous data, whereas in case of keyboard, so it is not that a big volume. So, it is a small amount of data. So, that way these devices they are of different nature. Okay. So, each of them has got its own controller. So, they are so the overall diagram that we can have is maybe like this. We have got one or more CPUs and a number of device controllers connected through a common bus. So, the situation is like this. So, we have got a bus from which I can have a number of CPUs, say C1 and C2 are two CPUs, and then we have got a number of device controllers. So, we call it DC1 device controller 1, DC2 device controller 2. To device controller 1 the actual device D1 is connected, to device controller 2 the actual device D2 is connected. So, individual devices can be memory chips, maybe disk drives, maybe keyboard, maybe mouse, any device that you can attach to the system. So, this interface has to be provided, connected to a common bus that provides access to shared memory. So, this memory chip is also there, as I said. Now, the memory locations need to be accessed. So, that way the memory access has to be provided. So, each device controller is in charge of a specific type of device, for example, disk drives, audio devices, video displays, and each device controller has a local buffer. So, as I said, for each device there is a device controller. Now, very often what happens is that for a number of devices they are of same type. For example, I may have say 3 disk drives in my system. I may have say a number of audio devices in my system. So, for them having separate device controllers may not be necessary. So, I can have a single device controller that can control all the audio devices, or similarly single device controller that can control all the video devices, all disk drives. So, like that. So, that way I can have device controllers of a specific type, and each device controller will have a local buffer. So, that any transfer that is going to take place between the computer system and the device driver or the device controller. So, they can be buffered there. So, as I was telling previously that when say one program is printing something onto the printer, another program also wants to print. Now, this print data cannot be allowed to go to the printer, but we can keep it in some local buffer, and so for the second program the content may be kept in a local buffer, and then later on when the printer is free that data may be printed. So, that is why we should have some local buffer available with individual controllers. CPU moves data from or to main memory to or from these local buffers. So, CPU does not view each of these devices in a separate fashion. So, they just the CPU's job ends by transferring the input output data to and from the buffer within the device controller. So, we have got if this is the device controller. So, within this device controller we have got the buffer. So, this is the buffer, and with this buffer, with this device controller the actual device is connected. So, the CPU does not send the data to the device directly, but it sends to this buffer, and from this buffer the device controller will be writing to the device. So, we have got this thing that each device CPU moves data from to main memory to from local buffers. The CPU and device controllers can execute in parallel. So, this is one good thing, like when the device the printer device controller is printing something onto the printer. So, CPU is free. So, CPU can do some other computation. So, they are executing in parallel. So, as long as they do not need to access main memory there is no problem, but at some point of time it may so happen that both of them need to access main memory. So, they will start competing for the memory cycle. This is more common if you have got multiple processes, multiple CPUs. So, they want to access memory, and there will be a fighting between them for getting access to the memory. So, to ensure orderly access of the shared memory, a memory controller has to synchronize the access to the memory. So, we need some sort of memory controller which will be making this access pattern proper, and it is not that one process request for a memory location content and it is given to some other process, that should not happen. So, all these are controlled by the memory controller. So, we also have got this different other devices, like say this is a typical situation of a modern computer. We have got this CPU and memory. So, these were there in the traditional computer, and we can have a number of IO devices like disk, mouse, keyboard, printer, monitor, etc. Out of this maybe in any most of the modern computer systems, so they have got, so this mouse, keyboard, printer, so they are all USB driven devices, and we can have some USB controller. Okay. So, so that this all these interfaces become standard interface. Though we are also have got USB disk, but so there are many disks which are not connected via USB because of speed limitations and all. So, there I can have separate some other type of disk and the corresponding disk controller should be present. Similarly, the monitors can also be USB driven, but the type of feature that the monitor has in terms of resolution, in terms of graphics capabilities. So, this basic USB may not be able to provide it. As a result, we keep separate graphics adapter that connects to the monitor. So, when this CPU looks into the system, so apart from the memory, so for all other devices it looks in a homogeneous fashion. So, whether it is a disk write or a writing onto the printer or writing onto the monitor, CPU issues similar type of command to the corresponding controller. Now, it is the controller's responsibility to translate it into the appropriate command for the underlying device and get it executed by the underlying device. So, modern computer systems, they will look something like this. So, any computer system, what happens when we start it up? So, we switch on the computer, then what happens? So, typically what happens is that there is a bootstrap program which is loaded at power up or reboot. So, in a so what happens is that if this is the CPU in the basic architecture that you have. So, there I said that there is a memory chip connected here and there can be multiple memory chips, and then a part of the memory is called read only memory or ROM, and another part is called RAM or random access memory. Now, read only memory, the point is that the content is not lost even if the CPU if power is off. So, it is there. So, what this CPU does? So, if you look into any processor, any microprocessor, so you will find that it tells that if you reset or power on this microprocessor, its program counter or PC gets some specific value. For example, if you are looking into 8085, so it gets the value all 0. So, that way depending on the processor, so this manufacturer they will tell what is the value of this program counter when the system resets. And as you know that when so if I in a microprocessor, if I switch on or if I press the reset button, program counter will get this value, and then at the next cycle what it does is that it puts the content of that program counter onto the address bus, and whatever be the content of the corresponding memory location, it gets loaded into the CPU, and that is taken as an instruction and executed, and then the content of the next memory location, the PC value, the program counter value is updated, and that is put onto the address bus, so that it gets the content of the next memory location until and unless the current instruction is a jump instruction. So, that way the process goes on. So, this operating system designers, they have to use this particular facility for locating the operating system and making the system to execute the part. So, the since the operating system is often very large, so it is not possible to hold the entire operating system into this read only memory. So, what is done is that only a very small part of it is loaded into is kept into this read only memory. So, which is called bootstrap program. The purpose of this program is to load so this computer system has got the disk connected to it. So, here the actual operating system is loaded here. So, what this bootstrap program will do? It will be copying this operating system from here and put it into the RAM when the system reboots. So, that is or the system boots when the system reboots or the power is switched on. So, this part of the program which is or with this part of the operating system which is kept in ROM or EEPROM is called firmware, because this is not fully hardware, but it is not fully software also, because I am not going to change it. So, this is something intermediary between hardware and software, and that is why it is called a firmware. So, the basic responsibility of this bootstrapping or firmware is to initialize all aspects of the system. So, it will it will initialize all the devices that you have the system, and then it will load operating system kernel and start execution. So, then it will, as I said, that the operating system is kept in a fixed location in the disk, and from there it will be loading the operating system, put it into RAM, and then from that point onwards system is fully functional and it starts operating accordingly. So, this is the computer startup process or the booting process. So, many times you may find, you might have noticed this error that this computer, the operating system could not locate the boot device. The reason is that what the bootstrap ROM has said, whatever address is given for the disk, maybe that disk is corrupted. So, it could not reach that particular point, or the disk may not be inserted into the system. So, previously when you have got in particularly the lightweight systems, where we have to boot it using some external disk or say or over a network like that. So, that is not done. So, now we have got the concept of this thin client and all, where this operating system is there in the server, and this thin client it has to load the operating system from the server. So, here the bootstrap or this ROM, the EEPROM or EEPROM that I am talking about. So, it will have some routine, so that it can access over the network the server that contains the operating system. So, there it is here the bootstrap operation is not copying from disk, but copying over the network. So, that way the meaning of this bootstrap operation may change as you go from one system to another system, but essentially it loads the important part of the operating system and starts executing the operating system. So, we have next we will be looking into the computer system operation. So, once the kernel is loaded and executing, it can start providing services to the system and its users. Now, the kernel has been loaded. So, any operating system can be thought of as a set of services, as from the user's viewpoint. So, you can think of an operating system as if it provides me a set of services, like it allows me to execute a program, it allows me to open a file, it allows me to read from the file or write onto the file or closing the file. So, like that any operating system can be viewed as a set of services. So, some services are provided outside of the kernel by the system programs that are loaded into memory at boot time to become system processes, or system daemons that run the entire time the kernel is running. So, some of the services they need to modify the system resources. So, as a new process is created, so process table has to be updated, a new file is opened. So, that way a file has to be updated, file table has to be updated. So, like that the kernel has to be updated. So, that is they are called daemons, system daemons, and there are certain services that are provided by the system. So, they are provided separately, like say compilation job or so like that. So, they may be system processes. So, on Unix operating system, the first system process is the process whose name is init. So, if you look into any Unix operating system and try to see what are the processes running in the system now at any point of time, you will find a process whose name is init. So, this is the first process that is created in the Unix operating system. So, this is when the system boots. So, this is the first process that is created and it starts other daemons. So, and then once this phase is complete, the system has fully booted and the system waits for some event to occur. So, normally if you boot a Unix operating system, you may find this type of messages onto the screen, the init and all, and then you can find that several daemons are getting started. So, this daemon starting is done by the init process, and then when it is completely booted, so then it comes up with a login message and it waits for some user to log in into the system and ask the system to do something. So, that way we can this system will wait for some event to occur, and when that event occurs, so it is the operating system is informed that an event has occurred, and accordingly the system takes care of that. The occurrence of an event is signaled by an interrupt. So, this interrupt may be a hardware interrupt, may be a software interrupt. So, we will see that signifies the occurrence of an event, and accordingly the system starts doing their operation. So, there are two types of interrupts, as I said, one is hardware interrupt and another is software interrupt. A hardware interrupt is a device may trigger an interrupt by sending a signal to the CPU, usually by way of the system bus. So, it is like this. Suppose I have got a keyboard connected to my system. Now, if the keyboard has to be operated, the user has to press some key at some point of time, and now you see that the computer system that we have or the processor that I have. So, that is an electronic device, this keyboard is a mechanical device, and the person who is operating it in most of the time is a human being. So, a human being has got an inherent speed limitation in which he or she can enter can place the characters on a keyboard. So, the electronic part or the processor part is much faster compared to this human being. Now, if the system is designed like this, that the processor will check whether the user has pressed some key or not, and it waits for that, then it becomes clumsy, because the user the processor is waiting unnecessarily for a long amount of time. So, one solution is that the processor may be doing something and periodically it comes back to check whether the user has pressed any key or not. But then the difficulty is that the response that the user will see is not very much deterministic. So, it will see sometimes that as soon as the key is pressed, it is responded to, because the processor has checked for the status of keyboard very soon, or at some point it may be the response is not that fast, because the processor was busy doing something else and it checked that keyboard status after a long time. So, that can happen. Now, the other solution to this is, as and when the user presses some key, the CPU is informed that a key has been pressed and the processor takes care of that. So, immediately, so processor suspends whatever it was doing and it comes to the it comes to the operation by which it can read the content of the keyboard. Now, this way, since the user cannot type at a very high speed, so the user will not be able to generate a large number of interrupts very fast. So, the overall system works very fine. Similarly, when we have to transfer some data from the secondary storage to the main memory or to the processor, then also the same thing. The secondary storage in most of the time is a electromechanical device. So, that way it takes time to read something, or an optical device that takes some time to get the data from transferred and all. So, the processor or the CPU should not wait for that much of time. So, when this processing is over, when the disk controller has done the transfer, then it may tell the CPU, okay, the transfer is over. So, you can take the content from the location. So, that way we can have some interrupt coming from the disk controller. So, this is one type of situation. Other type of situation is that a software may generate some interrupt. It is a program may trigger an interrupt by executing a special operation called a system call. Like while executing the program, maybe a program has given a statement like, say, to output something onto the printer. So, that requires services from the operating system. As I said, as we discussed previously, the printer is not given simultaneously to more than one process. So, that way it is a system call. Similarly, a program it wants to create another it wants to start another program. So, that way it has to get a service from the operating system. So, these are the interrupts generated by the software. A software generated interrupt is caused either by an error or a user request like IO request. So, this is other source of software interrupt that we have is the some error that has occurred, like say I have got say x, I have written a statement like z equal to x divided by y. Now, what if y is equal to 0? Okay. So, at the time of program compilation, so we could not check this because we did not know what is the value of y, but at the run time while this statement comes into execution, the hardware finds that y value is equal to 0. So, the division operation cannot be carried out. So, that is a divide by 0 error. So what the system will do when this occurs? So it must transfer the control back to the operating system, telling that a divide by 0 error has occurred, and then operating system should take appropriate action. So which action, that is of course different, that is dependent on the operating system and the user program, but this is a special situation. So an operating system is interrupt driven. So after doing the initialization part, the operating system actually waits in a loop for some interrupt to occur, and when some interrupt occurs, so it will be telling the it will be informing the system that okay, an interrupt has occurred, and then the appropriate action will be taken by the operating system. So this interrupt is another very important thing that this modern systems will have, so that we can do the operations done by the operating system. Common functions of interrupts. When an interrupt occurs, the operating system preserves the state of the CPU by storing the registers and the program counter. So this is the first thing that the system does. So it remembers like what it was doing, because sometime later it has to restart the operation. So it will be saving the content of the current state of the CPU, storing the registers and program counter, determines which type of interrupt has occurred and transfers control to the interrupt service routine. So whether it is a maskable interrupt or non-maskable interrupt, what is the priority of the interrupt. So based on depending many issues that you can get into, the discussion can be obtained in more detail in some computer architecture classes or microprocessor classes. So I am not going to that, but after determining the type of interrupt, that control will be transferred to the corresponding interrupt service routine. Interrupt service routine is nothing but a collection of modules or routines which are responsible for handling one particular interrupt. For example, a printer has given an interrupt that whatever printing job was given is over. Keyboard gives an interrupt that a key has been pressed, or a disk gives an interrupt telling that the disk transfer is over. So what the corresponding action should be, that is known to the system designer, and accordingly the operating system designer has written the corresponding interrupt service routine. So this interrupt that comes, it goes to the interrupt service routine, and accordingly the appropriate action is taken. The transfer is generally through the interrupt vector, which contains addresses of all the interrupt service routines. So for the entire system, for all the interrupts, to which address it should go, where is the actual interrupt service routine located in the main memory. So that is kept in the in a table called interrupt vector table, and from there these interrupt vector addresses are taken and it goes to the corresponding service routine. The interrupt architecture must save address of the interrupted instruction. So this is very important, because it has to restore when the interrupt is over, it has to restore the operation from there. So on the timeline, so you can say that for some time the user program is executing, then after some time the interrupt comes, like for example an IO device. So it was told to do some transfer, so it was idle for this much time, then it was transferring the data. When the transfer is over, it gives an interrupt to the processor CPU telling that transfer is over. So the processor goes into interrupt processing cycle. So in this time it is doing the interrupt processing, then again it is going into the service, it is going into the normal operation. So it is going like this. Then after some time again another IO request is made by the processor, by the CPU, by the program. So when the IO request is made, the device is informed, and the device makes a transition from idle state to the transferring state. So again after it starts doing the transfer, when the transfer is over, it sends an interrupt to the processor or the CPU, and after some time CPU goes into the interrupt service routine, executes the interrupt service routine in this part. So this way it goes on. So transfer is initiated by the CPU. After the device has done the transfer, it gives an interrupt to the processor telling that transfer is over. Now the processor goes into the interrupt service routine to decide what exactly has to be done for the particular operation. So this overall flow is like this. The CPU device driver initiates the IO transfer, that is first step number 1. In step number 2, for the IO controller, so it initiates the IO operation. step number 3, input ready, output complete or error generated, etc. So, some IO operation is over at this point. So, it sends an interrupt to the processor. So, in between CPU is checking for executing checks for interrupts between instructions, or the interrupt has occurred between two instructions or not. So, those checks are done. So, when this interrupt comes, so CPU receives the interrupt and transfers control to the interrupt handler. In turn, the interrupt handler will process the data and return from the interrupt, and then after that, when the interrupt is over, it will, the CPU will resume from processing the interrupted resume to processing the interrupted task.